Hello, everyone. So today we're going to be talking about the relationship between pressure and volume when it relates to gases. And that relationship is known as Boyle's law, which we'll get more into later on in this presentation. So in order to really dive into this, we need to understand what pressure and volume are. Volume is pretty self-explanatory, right? It's the amount of space something takes up. If there's more space, that's a larger volume. A smaller amount of space is a smaller amount of volume. Pressure, we've experienced pressure, right? If you push on something, you're exerting pressure. The harder you push, the more pressure there is. But the pressure when it comes to gases has to do with the individual gas molecules and how they're interacting with their environment. So the pressure from a gas comes from molecules bouncing around and hitting off the inside walls of whatever container they are in. The more frequent those hits and the more forceful, so the faster the molecules are going, the higher the pressure. And so if you change the volume of your container, that in turn will affect the pressure. And so we're going to figure out how it does that, and we're going to use the PhET simulation that I showed you guys the other day. So there's a link here for when you guys click on the PowerPoint later on, but I will pull that up. And here we have our simulation. So we have our container, right? This container here is the volume of the container, and we have a gauge here that measures the pressure. Right now there's no gas inside, therefore there is no pressure being exerted. We can pump in some gas molecules, let them bounce around, and we'll see, right, these gas molecules, they are hitting the walls of the container, bouncing back and forth, and they establish a pretty standardized pressure, right? It's around 58 atmospheres or ATM. So right now, our width is about 7.0 nanometers. If I decrease the volume, right? If I make my container smaller, think about it. How do you think that will affect the pressure or the amount of times that our molecules are hitting the walls? And so while you're contemplating that, we have a collision counter here, right? And that will help us really get a number to go with the collisions or the amount of molecules that are hitting the sides of the walls here. At 7.0 nanometer width, if we test out the number of collisions, it tells us we're at about 464. Our pressure is at about 58 here. So if we decrease the volume, if we go from 7 to, let's say, 5 nanometer width here, we have the same amount of gas inside, but now we have less space for them to bump around, right? So the number of times that they're hitting the walls, remember we were at 464, now we're at a little over 700, right? So we increased the amount of times that these molecules are hitting the walls of their container because we decreased the size of the container. And in doing that, the pressure went up from, I believe it was like 58, all the way up to 81, right? So the pressure goes up because they're hitting the sides of the container more and more frequently because the container is smaller and there's less space for them to move around. Now on the flip side, right, we're at 5 nanometer width here. What if we double it, right? We're going to double the size of our container, go up to 10. Remember these numbers, 700 approximately wall collisions and about 81 atmospheres of pressure. If we double the volume, right, so we're increasing the size of our container, let's test out the wall collisions again. It's a little under 350, right? So it's about half as much. So we doubled the size of the container, and the number of wall collisions decreased by that same factor of 2. And if you look at our pressure, right, we went from 81 to about 40 and a half or 41 here. So the pressure also decreased by that factor of 2, even though the volume was increasing by twice as much. So this is Boyle's law as we know it, right? As you increase the volume, the pressure is going to decrease by that same factor. And as you decrease the volume, the pressure will increase by that same factor. Going back to our lesson here. Boyle's law was discovered by a man named Sir Robert Boyle, and he found that there was an inversely proportional relationship between the volume of a gas and the pressure it exerted. So we have this graph here, right? As the volume increases, as we get bigger and bigger, the pressure, or our y-axis, goes down. And the same as for the inverse is also true, right? As you go to the left, as the volume gets smaller and smaller, the pressure goes up. So inversely proportional means that if you cut the volume in half, the pressure is going to be doubled. And in our example we just did, if you double the volume, the pressure was cut in half, right? So it's inversely proportional, meaning if one goes up, the other goes down by that same factor. So again, as you decrease the volume, the pressure increases because the molecules are hitting the sides of the wall more and more frequently. Then as you increase the volume, the opposite happens. The pressure goes down because there's more space for the gas to move around without actually hitting the walls of the container. And so Boyle's law, the equation for it, looks like this. We have P1 times V1, so P stands for pressure, V stands for volume, 1 stands for initial, just like in previous equations we've done, and then equals P2 times V2. That is our new pressure and our new volume. So when we do examples with this in a moment, you'll see that there's an initial set of data and an after or later set of data. And we're going to be missing one of these 4 variables here, and we can plug in and solve using a little bit of algebra. So why does this matter? Where do we see Boyle's law in everyday life? Well, we've been breathing as we've done, or as we've been watching this, and our lungs use this concept, right? So we can't actually suck in air. You can't do that naturally without using this concept or this gas law. What happens, how our body works, is our diaphragm, that's what we call like our rib cage and the muscles around our lungs. What we do is we expand them using our muscles, right? And as we expand, it expands our lungs. That means that the volume goes up, right? We're increasing the volume of our lungs. And in doing that, because the volume's going up, the pressure inside of our lungs is going down, right? And naturally, gases like to have the same pressure everywhere as best they can. There's an old saying that nature abhors a vacuum, right? Vacuums don't exist naturally because gases and liquids will go and fill up that vacuum. So our lungs are creating almost a vacuum of sorts based on Boyle's law. And it sucks in air through our nose, through our mouth, through our throat until it fills up our lungs and they're equal pressure with the outside environment. And then to expel that air, right, we contract, meaning we decrease the volume of our lungs, and then that makes a high pressure environment in our lungs, which is expelled back out of our mouth. So that's how our lungs work. That's how a lot of things work. Syringes, right, are another great example of this. We've all hopefully seen a syringe at some point. How a syringe works, how you can suck stuff up, is by increasing the volume here. You can increase it by pulling this out and decrease it by pushing it in. So there's no needle or anything on this, it's just a little hole. If I cover that hole, and then I try and push this together, I can do it to a certain extent, but then it gets really difficult because there's a lot of air pressure in here. I'm decreasing the volume, so the pressure is going up as I do that, right? If I let go, it gets shot backwards from that pressure. Or if I do it again and let go of my finger, you can see that, or here, the gas escaped really quickly. The opposite's also true, right? If I put my finger over it, there's a small volume initially, and I pull, I can do it to a certain extent, but it gets really, really difficult. And my finger, I can feel that's being sucked into the little hole right there. And I can't really pull it all the way out because of the air pressure being really, really low on the inside and really, really high on the outside. So it sucks it back in. So one thing I would normally have you guys do in class is you'd all have one of these. You can mess around with it like I just showed you. And there's also mini marshmallows that we get to play around with. If you guys want to do this next year, come find me and we can make it happen. But if you put the mini marshmallow into the syringe, marshmallows are just sugar pretty much, but filled with air, right? They're aerated. So there's lots of air inside the marshmallow. So you'll see, try and make this as visible as best I can. I have a mini marshmallow inside of my syringe. If I cover the end and then press it in, you'll see the marshmallow starts to get smaller, right? It almost shrinks as you press it in. That's because I'm decreasing the volume. The pressure is going really, really high, and it's pushing in the marshmallow. And the opposite is also true. Let's see if I can make it bigger for you. If I start with a small volume and pull instead, the marshmallow gets bigger, right? Then it goes back to how it was before. But because I'm decreasing the volume, which is sucking out the air inside the marshmallow. So now that we're big, I'll do the first one again, right? If I push in, there's a lot of pressure, the marshmallow gets smaller, and vice versa. Okay, and there's a great YouTube video, there's tons of them on YouTube, with vacuum chambers. I don't have one in my house right now, but I'll link it here, and if you guys want to watch it later on, it's worth watching. So when it comes to the actual calculations, we're just using this pretty simple equation here, right? So here's an example of a problem that you would see where you could use Boyle's law. So if we have a balloon that has a volume of 1.8 liters and an internal pressure of 780 torr. So remember, there's lots of different pressure units. Torr is one of those pressure units. The balloon is then squeezed, right? So if you squeeze a balloon, you're decreasing the volume. It's squeezed to a new volume of 1.3 liters before it pops. So once we get to 1.3 liters, it can't take the pressure anymore and it pops. We want to know what the internal pressure of that balloon was when it popped. And to do that, we would use this equation here. So again, just like all the other equations we've used throughout the year, it's just like a little game of Where's Waldo? You find each of these numbers, you find which one of these they belong to, you plug them in, you solve for the one you don't have. So I like to just start from the left and work my way across. My P1, again, P stands for pressure, 1 stands for initial. So my P1, my initial pressure, if I read through here, it says a balloon has a volume of 1.8 liters and an initial pressure of 780 torr. So my P1 would be 780 torr. My V1 is that initial volume, being 1.8 liters here. So P1 is 780 torr, V1 is 1.8 liters. Now we have the left-hand side of our equation. On the right-hand side, we would find P2. So the rest of the problem says the balloon is squeezed to a new volume of 1.3 liters. So that's going to be our V2 is 1.3 liters. And then it says, what was the initial pressure or the internal pressure of the balloon when it popped? So P2 is going to be our variable. That's what we're trying to find out, is the new pressure. V2 is 1.3 liters. So now, once we have all these and our one variable, we just plug them into our equation here, right? So P1 would be 780 torr, V1 would be 1.8 liters. That's equal to, P2 is our variable, so we just keep it as P2. That's what we're going to be solving for in a moment. V2, oops, there should be a 2 right here, but V2 is 1.3 liters on the right-hand side. So now to solve for P2, all you do is get rid of the 1.3 that's on the same side. These are multiplied together, so to get rid of it, you would just divide both sides by 1.3. You end up with P2 equals 780 torr times 1.8 liters divided by 1.3 liters. Our liters units cancel. When you plug this into your calculator, you end up getting 1080 torr as the internal pressure of the balloon. So this, according to our one test here, was the maximum internal pressure that our balloon could handle, which is important information if you're a balloon developer or something like that, or you need to use a balloon for something. So that's how you use Boyle's law. We'll have some simple examples in our homework, but if you have any questions, feel free to watch the video again, ask me, email me, and if you want to go back and watch that video that I linked, it's great. It's short, it's like 3 minutes, and it's pretty exciting using a vacuum chamber with some marshmallows. Otherwise, have a good rest of your day.